Today we're going to be looking at a particular problem and trying to understand better some of the calculus notation that we're going to become familiar with. In this contextual problem, traffic flow is defined as the rate at which cars pass through an intersection measured in cars per minute. Notice those are rate type of units. The traffic flow at a particular intersection is modeled by the function f defined by, and then they give us this function for time values from 0 to 30, where f of t is measured in cars per minute, and t is measured in minutes. So, to begin, let's say a student were to find f of 10. How can we interpret the meaning of this? Well, this is going to be the rate at which cars pass through the intersection at t equals 10 minutes, measured in cars per minute. So I'm going to write, this is the rate at which cars pass through an intersection measured in cars per minute at t equals 10 minutes. Okay, now if we were to find f prime of 10, well, now we've taken the derivative, which is a rate of change, of something that's already a rate of change. So I'm going to interpret this as the rate of change in the rate at which cars pass through an intersection in, this is where it gets tricky, cars per minute per minute. Notice we have something that was already a rate, and then we've done another rate on top of that. We're not quite done. At t equals 10 minutes. In interpreting the meaning of calculus notation, leaving out the time is one of the most common mistakes. Okay, now let's look at some other possible things that we might do. The AP question asked students in Part A, to the nearest whole number, how many cars pass the intersection over the 30-minute period? Well, remember that what we have is a rate, and if we integrate the rate of change, we should get an amount. So we would be integrating from 0 to 30, f of t dt, and a quick analysis of units here, remembering that f of t is measured in cars per minute, and we're multiplying by the differential, which is measured in minutes. This should give us an answer, which is the number of cars that pass through the intersection during this 30-minute time interval. What else could we do with an integral? Well, if we'll look down here to Part C, another part of the question asks, what is the average value of the traffic flow over the time interval from 10 to 15 minutes? Well, whenever I hear the word average, I think I should add and divide. I'm going to add from 10 to 15, and I'm looking for the average of what? The traffic flow, which is f of t dt, and I'm going to be dividing by 15 minus 10. You should probably recognize this as being an average value integral. Let me double check my units. F of t is measured in cars per minute. My differential is measured in minutes, and then I also have 15 minus 10 minutes. Notice these minutes divide out, and my answer is going to be cars per minute. Notice they asked to indicate units of measure. We're looking for the average value of the traffic flow, and the traffic flow is the rate at which cars pass through the intersection. It's a rate. That's why the units need to be cars per minute. Notice the next part of this question. It says, what is the average rate of change of the traffic flow over the time interval from 10 to 15? And again, indicate units of measure. Well, in order to find an average, I know I always want to add and divide. Again, from 10 to 15, and I'll have 15 minus 10 down here. How is this different from the last one? Well, notice that in the previous part, we were looking for the average value of the traffic flow. So our integrand was just f of t. Now we want the average rate of change of the traffic flow. And so this phrase here, rate of change, indicates that we need to be doing a derivative. Let's figure out the units for this. Earlier, I said the units for f prime of t would be cars per minute per minute. Right here, this differential is measured in minutes, and then we have 15 minus 10 minutes. There are minutes all over the place on this thing. Let's go ahead and divide these out, and we'll have cars per minute, which can also be written as cars per minute squared. Notice we were doing a rate of change in something that's already a rate. Uh-oh, I went off the screen a little bit. Okay, let me just slide that over so you can see what I wrote. Thanks for listening and enjoy calculus.